So we already have quite a bunch of numerical methods for the Cauchy problem. We've previously seen how to compute the local discretization error for the explicit Euler method and the implicit Euler method. And now we're going to do just the same for the explicit midpoint method, the implicit midpoint method, the Crank-Nicholson method, and Horn's method. I've been very much looking forward to this because typically you do not find the derivations of the local discretization errors for all of these methods at one place. Most textbooks are going to give you formal proofs for the local discretization errors for only a few of those methods. We're going to have a deep analysis of the local discretization errors, however, for all of these four methods. And you will recognize that the techniques applied are actually quite similar. As we compute the local discretization errors, we can apply the theorem from the previous video, which shows us that for any estimate for the local discretization errors, we also obtain a corresponding estimate for the global discretization error. Given any numerical method, we only need to compute an estimate for the local discretization error, and we get an estimate for the global discretization error for free. Since the proof techniques are very similar, let us fix a few assumptions and some notation. First, we impose our usual continuity condition. We assume that we have L non-negative, such that for all times t and all x and y in R to the n, we have ftx minus fty in Euclidean norm is bounded from above by L times the Euclidean norm of x minus y. Furthermore, since we are talking about the local discretization error, we always compare our numerical method to the exact solution of an auxiliary problem. So having defined UK in the case iteration step, we take a look at the Cauchy problem v prime of t equal f t v of t with initial condition v at time tk equal uk. That's just how we have done with the definition of the local discretization error. This time we call the solution to this auxiliary problem v. And in all the following calculations, we are comparing v at time tk plus 1 to the approximation uk plus 1 produced by the numerical method. We also assume that irrespective of the time, we have a bound on the derivatives of v. Specifically, we assume that we have two constants, non-negative constants, c2 and c3, such that the Euclidean norm of v prime prime for all times t is bounded by c2, and the norm of v prime 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 for all times t is bounded by c3. So I assume I have some uniform bounds for the second and the third derivative of v. Before we begin, let me remark that the error estimates that we are going to find apply for vector-valued Cauchy problems, but we only write down the proof for scalar-valued Cauchy problems. The reason is that taking into account vector-valued Cauchy problems would unnecessarily complicate the notation. We are going to write down the proofs in a way such that the vector-valued versions are easily obtained by some small modifications. Let us begin with analyzing the local discretization error for the explicit midpoint method. So suppose we have our iterate UK, we have computed UK plus 1, and then the local discretization error, by definition, is the difference between v at time tk plus 1 minus uk plus 1. We plug in the definition of uk plus 1 for the explicit midpoint method, and so this error equals v at time tk plus 1 minus uk minus h times f at tk plus h over 2, uk plus h over 2 f tk uk. And next we use that uk is precisely the value of v at time tk. Furthermore, let's take a look at this term uk plus h over 2 ftk uk at the very end of this expression. That is a step of the explicit Euler method with half a step size. But it can also be seen as a Taylor approximation of v at time tk plus h over 2. The Taylor development around time tk. And using our error representation formula for the Taylor development of first order, we now get to the following result, namely the local discretization error equals the difference v tk plus 1 minus vtk minus h times f at tk plus h over 2 and vtk plus h over 2 minus h square over 8 v prime prime psi for some psi that is somewhere in the time interval from tk up to tk plus 1. In this very last step, I've simply used the Taylor approximation theorem. Now we notice that the first difference here, vtk plus 1 minus vtk, coincides with the integral of v prime over the time interval tk up to tk plus 1. And then what we subtract, h times this evaluation of f, could be seen as just the midpoint rule approximation for that integral, where the midpoint of the interval is tk plus h over 2. If it weren't for this term h square over 8 v prime prime psi. At this point we use that f satisfies our continuity condition. So we take norms of the local discretization error. So we take a look at the Euclidean norm of the magnitude of vtk plus 1 minus uk plus 1. And that can be bound from above as follows, namely by the magnitude of vtk plus 1 minus vtk minus h times f at tk plus h over 2 vtk plus h over 2. And then using the continuity condition of f, we get the additional term plus L times h cubed over 8 times the size of v prime prime psi. To simplify that, we use the ordinary differential equation that is satisfied by v, and so the term in the norm can be simplified to vtk plus 1 minus vtk minus h times v prime at time tk plus h over 2. So in particular, that term is now the difference between the integral of v prime from time tk up to tk plus 1 minus the evaluation of the midpoint rule applied to that integral. Okay, next we use the error estimate for the midpoint rule. There exists a zeta somewhere in the interval tk up to tk plus 1, such that the following is true. The difference vtk plus 1 minus vtk, as we recall, is the integral from tk up to tk plus 1 of v prime. And that coincides with h times v prime at time tk plus h over 2, which is the formula for the midpoint rule, plus the error term h cubed over 24 times v prime 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 zeta. So simplifying all that, we get that the magnitude of the local discretization error, vtk plus 1 minus uk plus 1, is bounded from above by h cubed over 24 times the size of v prime 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 at zeta plus L h cubed over 8 times the size of v prime prime psi. Since there's generally no way of knowing zeta and psi in this formula, we simply estimate the size of the derivatives from above using our assumptions. So in total, what we get is that the magnitude of vtk plus 1 minus uk plus 1, the magnitude of the local discretization error, is bounded from above by h cubed times the constant c3 over 24 plus L times C2 over 8. The thing that matters most here is the cubic power of H. Different proof techniques might give you different factors, and typically nobody cares about those factors too much. But what people care about is this cubic power of H. So as H goes to 0, the local discretization error converges to 0 with cubic order. Having analyzed the error for the explicit midpoint method, let's do the same for the implicit midpoint method. So again, we start with the local discretization error, v at time tk plus 1 minus uk plus 1. And using the definition of uk plus 1 in the implicit midpoint method, we write this as vtk plus 1 minus uk minus h times f at time tk plus h over 2 and uk plus h over 2 f at time tk plus 1 half uk plus 1 half. Here in that case, uk plus 1 half is that intermediate iterate to be used in the computation for the implicit midpoint method. Okay, in the next step, again, we replace uk by vtk, just as for the explicit midpoint method. And then for this intermediate iterate in the last argument of f, we use the error estimate for the implicit Euler method. We can rewrite the local discretization error as v at time tk plus 1 minus v at time tk minus h times f at tk plus h over 2 vtk plus h over 2 minus delta, where delta is the local discretization error in the implicit Euler method, corresponding to the step size h over 2. In order to pull off something similar as we have done for the explicit midpoint method, we need to get an estimate of this delta. Now we recall that the size of delta is bounded from above by 1 minus L times h inverse times h squared times v prime prime psi, where psi is somewhere in this time interval from tk up to tk plus 1. Under the condition, of course, that h is strictly less than 1 over L. I'm really just recycling here the estimate for the local discretization error of the implicit Euler method. Okay, now we can pull off something similar as we've done. I find that the size of vtk plus 1 minus uk plus 1 is bounded from above by the following expression, namely the norm of vtk plus 1 minus vetk minus h times f at tk plus h over 2 vtk plus h over 2. And then this additional term plus L times h, the size of delta. Okay, and let's plug in the size of delta, so that additional term becomes L times 1 minus LH inverse times h cube times the size of v prime prime xi. Okay, now the term in the norm can be simplified. Then we see that we've got the difference of vtk plus 1 minus vtk minus h times v prime at time tk plus h over 2. And the term in the norm is again the difference of the integral of v prime over the time interval minus the approximation of that integral by the midpoint rule. So just as before, this difference vtk plus 1 minus vtk is just the integral from tk up to tk plus 1 of v prime, and that is equal h times v prime at time tk plus h over 2. It is just h times v prime at the midpoint of the interval, and then plus this error term, h cubed over 24 times the size of v prime 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 at some zeta where zeta is somewhere in this interval tk up to tk plus 1. The norm of the local discretization error for the implicit midpoint method can be bounded from above by h cubed over 24 times the size of the third derivative of v at zeta, and then plus L times 1 minus LH inverse times H cubed times the size of V prime prime psi. Just as before, I apply the estimates for the derivatives, since I don't know psi and zeta in practice, and I get that the norm of the local bounded from above by H cubed times the term C3 over 24 plus 1 minus LH inverse times L times C2. Again, what matters here is this cubic power of H. And if you use slightly different proof techniques, this last factor will be slightly different depending on what you do. But typically that is of lesser importance in numerical analysis. So we've analyzed the local discretization error for two numerical solvers for the Cauchy problem, namely the explicit midpoint method and the implicit midpoint method. These are based on the midpoint rule, and now we're going to take a look at the two numerical solvers that we based on the trapezoidal rule. Let's have a look at the Crank-Nicholson method. So we recall that at each direction, UK equal UK plus H over 2 times FTK UK plus FTK plus 1 UK plus 1. Just as before, the local discretization error is VTK plus 1 minus UK plus 1 by definition. Let us plug in now the definition of UK plus 1 in the Crank-Nicholson method. And so we see that the local discretization error equals V at time tk plus 1 minus UK minus H over 2 times FTK UK plus FTK plus 1 UK plus 1. Now we note again that UK is just the initial value of V at time tk. So we make that substitution. And then to apply something similar as we've done for the error estimate midpoint method, we would like to get rid of that last UK plus 1 in the argument of F and replace it by VTK plus 1. Okay, the least thing I can do is to replace UK plus 1 by VTK plus 1 plus the difference UK plus 1 minus VTK plus 1. Just some algebraic substitution. I haven't changed anything yet. Okay, using the continuity condition of F and the trying inequality, we make the following estimates, namely the size of the local discretization error is bounded from above by the norm of VTK plus 1 minus VTK minus H over 2 times F at TK VTK plus F at TK plus 1 VTK plus 1, and then an additional term plus H over 2 times L times the norm of UK plus 1 minus VTK plus 1. Now we are in the position to apply the differential equation to the first term. So we see that this first norm equals VTK plus 1 minus VTK minus H over 2 times V prime at time tk plus V prime at time tk plus 1. We see that the term in the first norm is just the difference of the integral of V prime over the time interval and the approximation of that integral by the trapezoidal rule. Next, we apply an error estimate for the trapezoidal rule. So we still have that vtk plus 1 minus vtk is the integral from tk up to tk plus 1 of v prime. And that integral equals the approximation, or by the trapezoidal rule, up to some error term. Namely, it equals h over 2 times v prime at time tk plus 1 plus h over 2 v prime at time tk minus h3 over 12 times v prime 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 zeta, where zeta is somewhere in the time interval from tk up to tk plus 1. Okay, taking norms and estimates, I get that the norm of the local discretization error is bounded from above by h cubed over 12 times the size of v prime 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 zeta, and then the term we had before, plus h over 2 times L times the norm of uk plus 1 minus vtk plus 1. And as you notice, that last term is actually just the local discretization error again. Now to handle that, let us assume that h is small enough. In particular, it's sufficient that h is smaller than 2 over L. Then I can pull off this norm of the local discretization error on the right-hand side, and I get the inequality 1 minus h over 2 times L times the norm of the local discretization error is bounded from above by h3 over 12 times the size of v prime 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 zeta. Okay, rearranging and taking estimates, I get that the norm of the local discretization error, the norm of v tk plus 1 minus uk plus 1, is bounded from above by 1 minus h over 2 times L inverse times c3 over 12 times h cubed. For this last inequality, I've divided by 1 minus h over 2 times L, which I can do if h is small enough, because then it will just be 1 minus some small term. So in particular, then it's going to be something positive. Okay, again, what matters here is that we have this cubic power of h. And I would like to remark that terms like 1 minus h over 2 times L inverse are quite typical of error estimates of implicit methods. The Cring-Nicholson method is an implicit method based on the trapezoidal rule, and Horn's method is an explicit method based on the trapezoidal rule. Okay, let us start by recalling that uk plus 1 in Horn's method equals uk plus h over 2 times f tk uk plus f tk plus 1 uk plus h times f tk uk. So in order to get the local discretization error for the Horn's method, let us start by just writing down the local discretization error, v tk plus 1 minus uk plus 1. And okay, of course we substitute uk plus 1. So this equals v tk plus 1 minus uk minus h over 2 times f tk uk plus f tk plus 1 uk plus h times f tk uk. Then we substitute that v at time tk is just uk, which gives the next step. And then we apply an error estimate for this application of the explicit Euler method. So we see that uk plus h times f tk uk equals v at time tk plus 1 up to some error term h over 2 times v prime prime xi, where as usual xi is somewhere in the time interval from tk up to tk plus 1. Okay, that instance of v tk plus 1 that we feed into f looks quite good. We just need to do something about the error term. So taking norms and applying the trying inequality and the continuity condition of f, we get that the norm of the local discretization error is bounded from above by the norm of v tk plus 1 minus v tk minus h over 2 times f tk uk plus f tk plus 1 v tk plus 1. Okay, now we can use the differential equation. We can modify the first term. So we have the norm of v tk plus 1 minus v tk minus h over 2 times v prime at tk plus v prime at tk plus 1. And we see again that is the difference of the integral of v prime over the time interval and the result of the trapezoidal rule applied to that integral. Let's apply the error estimate for the trapezoidal rule. So we have that the difference v tk plus 1 minus v tk equals the integral of v prime from tk up to tk plus 1. And that equals the result of the trapezoidal rule plus some error term. In particular, it equals h over 2 times v prime at time tk plus 1 plus h over 2 times v prime at time tk minus h cubed over 12 v prime 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 zeta for some zeta between tk and tk plus 1. Okay, now the techniques that we apply are fairly standard. Namely, we see that the norm of the local discretization error is bounded from above by h cubed over 12 times the third derivative of v at zeta plus L times h cubed over 4 times the size of v prime prime xi. Now, to simplify this, I apply the estimates on the derivatives, and I get that the norm of the local discretization error, the norm of v tk plus 1 minus uk plus 1, is bounded from above by c3 over 12 plus L times c2 over 4 times the cubic power of h. And of course, what matters is the cubic power of h, the cubic power of the step size. Up to now in this numerical analysis class, we've seen the explicit Euler method and the implicit Euler method. We've seen now the explicit midpoint method and the implicit midpoint method, and the Crank-Nicholson method and Horn's method. And for each of those, we have derived upper estimates for the local discretization errors. Those estimates are listed on this slide. I'm not going to read them aloud at this point. What matters, however, are the powers of h, and those I would like to discuss briefly. So the explicit Euler method and the implicit Euler method are comparatively easy numerical methods. Their local discretization errors are bounded by a square power of h times some constant, which nobody cares about actually. So as h goes to 0, the local discretization error is going to converge to 0 quadratically by order 2. Now, by comparison, these 4 new methods that we have found recently, based on the midpoint rule or the trapezoidal rule, have error estimates that involve a cubic power of h. Again, times some constants that are not that important. What matters is that as h goes to 0, these discretization errors will converge to 0 by cubic order. In particular, they will converge faster to 0 than the explicit or the implicit Euler method. That corroborates our observation that these 4 numerical methods deliver better results than the explicit and implicit Euler method for the same step size. Another reason to care about the local discretization error is their relation to the global discretization errors. Namely, these bounds on the local discretization errors will lead to bounds on the global discretization errors. That's just some result we've seen recently. Essentially, what matters here is that I check the upper bounds for the local localization errors, reduce the power of h by 1, and then multiply some particular factor, which we have seen is exponential of L times tk minus t naught minus 1 times the inverse of L. So as we compare the performance of these different numerical methods, similar observations apply as for the local discretization errors, namely the upper bound for the global discretization error for the explicit Euler method and the implicit Euler method converges linearly to 0 as the step size goes to 0. Whereas for these new numerical methods, I even get quadratic order. The upper bounds for the global discretization errors are bounded by some multiple of h square. We get all those upper bounds for free by our abstract theory that relates local and global discretization errors. And personally, I think this is tons of fun.